Actually, now that I think about, I'm sorry. I think that would be good.
Yeah.
I think you should have them in there somewhere. You don't have to. You don't have to put them with, but at some point you should print all those out and get them in the binder. Yeah. Otherwise, like if you go back to look at them later, you won't know what the questions answer. Okay, so number 15. I'm going to try to draw this, so everyone be perfectly quiet while these 3D problems are so hard to draw. Okay, that's a gear. I'm not going to try to draw the gear teeth. Perfectly silent. Okay. So far, so good. Yeah. Okay, talk a little more. That's making me uncomfortable. That drawing really makes it clear how much coffee I've had today. Okay, so you have these two gears. Those are the big discs. And they are along this long shaft that's mounted to the ground in two places, here and here. And there are forces applied to these gears, like there would be if these gears were actually turning some kind of machine or something. There's a force of 96 pounds and a force this way of 265 pounds. And then over here, there's a horizontal force that way of 192. And an upward force of 530 pounds. Okay. The gear on the left has a radius of 1.5 inches. And the gear on the right has a radius of 0.5 inches. And then the distance is this distance is 4 inches. This looks bigger, but it's 3 inches. And this is 2 inches. And we want to calculate the reactions. Okay, well, these are both pin joints, this and this. So that shaft is free to rotate in there. Yes? The middle. Yeah, that goes through the middle. I'm sure y'all remember this because you did it for today. That was a joke. At my own expense. Okay, so it's free to rotate in those 2 pin joints, but those pin joints are going to apply other loads, and we're going to figure out what loads they apply to the shaft. And this would be useful if this was some kind of machine and you were trying to figure out what to build those bearings out of, or, I guess that's what it would be in this case. Okay, so let's do this. And the coordinate system on these 3D problems, I think, except in one case on this set of problems, I'm just using drawings from a textbook. And so they always give you a coordinate system, and that coordinate system is usually, I think, in all these cases, chosen. It's a good choice of about point 2. There's no reason the origin has to be the about point, but it does make it a little simpler in this case. So this is what they call the z-axis. Up is the y-axis. And then the x-axis has to go out that way. All right. So what are we going to isolate? I think a good choice here. So, and also those gears are connected to that shaft. Those gears can't spin freely around the shaft. Okay. So I'm going to isolate the shaft and the 2 gears. Something like that. And the loads we have, well, we have the ones that are given. So the horizontal one here is 192. The vertical one is 530. Over here we have the downward force of 96. And the horizontal one of 265. And now we have to think about what kind of loads those pin joints apply. So there are a couple of kinds of pin joints in 3D. There are pin joints that apply thrust and pin joints that don't. It doesn't say anything, so on a lot of these it'll tell you which pin joint applies thrust, which one doesn't. In this case, it doesn't say anything about that. It's not going to matter in this problem, though. Why is that? It's not going to come up. Yeah. Yeah, right. So since there are no forces trying to make it go along the axis of that shaft, no horizontal force would have to be applied by either of those anyways. So we might as well just treat them as neither of them having thrust. And then a pin joint without thrust can apply up to 4 loads. It can apply 2 components of force, and then it can also, and it always applies those 2 components of force, but it can also apply 2 components of couples. So are we going to use those couples in this case? No, we're not, and that's because in this problem we have 2 pin joints with the same axis. And if you have 2 pin joints sharing the same axis, you ignore those couples. Okay, the forces will take care of the control of the orientation rather than those couples. Anybody have any questions about that? Yes. Mm-hmm. We don't know the mass, right? And so if it doesn't give you the mass, then it means that the weight is negligible compared to the other forces. And so we just leave it off. Like you could imagine the weight of that thing being like a tenth of a pound or a pound or something, and it's so much smaller than the other forces, it won't really change any of the answers. Yeah. Yes. Okay, yes. So, so if you have a pin joint without thrust, it always produces two force components, always, and then it can also produce two couples. But if your problem has two pin joints that share the same axis, you ignore those couples. And the reason is, so imagine this wasn't here, okay? And imagine that you tried to pull this shaft down, like rotate it about the z-axis, okay? And you'd be relying on this one pin joint to produce a couple that keeps you from rotating it down. Although you'd probably look at that and think like, I don't want to depend on that too much. I'll just rip that thing right off the floor, right? But if you have two of these together, you're not asking this one to produce a couple anymore. If you try to pull this down, rotate it around Z, the forces over here will prevent it for you. And you're not going to depend on those couples, okay? And same thing over here, like if this wasn't here and you try to pull on it, this would have to produce a couple. But if this is here, you pull on it and that force is enough to do it.
That makes sense. I just wanted to worry.
Okay, yep. All right, so the last thing we have to do is put in the forces that those pin joints apply. And so we have these two force vectors. I'll call that, well, they call that the joint C, so I'll call that RC. And that's a Y and a Z component. And then over here, same thing. So I'll call this RD. Okay, now that's everything. So rho, force, moment. And our about point is going to be over here. So first, the rho vector for that force RC is 0. The force vector, we don't have any x component because there's no thrust. The thrust is the force along the axis. So we have 0, and then RCY, RCZ. And the cross product is 0. And then we have the force. We can treat this as a force vector. These are two components. 96 pounds in the negative y direction, 265 pounds in the positive z direction. And the rho vector for that is the vector from this red dot to where that force is applied. So that's 4 inches. We'll travel positive 4 inches in the x direction. And then we'll travel the radius of that circle in the y direction. The radius of that circle is 1.5 inches. So this rho vector is 4, 1.5, 0. And then the force vector is 0x, negative 96y, and positive 265z. Cross product, I can't do that in my head. Can someone tell me what that is? And then we get to that force RD. The rho vector is, that's just 7 inches in the positive x direction. So 7, 0, 0. The force vector is 0 r d y r d z. And then the cross product is 0. And then negative 7 r d z. And then positive 7 r d y. And then the last one, so what's the row vector from our about point to where this force is applied? That's in positive x direction, 9. That's to get to the center of that circle. And then 0.5 in the positive z direction. So 9, 0, 0.5. And there's a force of 530 in the positive y direction and a force of 192 in the negative z direction. So positive, so 0x, positive 530y, negative 192z. And then can you compute those?
Negative 265, 1728,
Okay.
and 4770.
4770. Okay. All right, so now we have that whole table done. Now we can do Newton's laws. Newton, the first component. Yes, that should be negative. Okay, so Newton's second law says 0 RCY RCZ plus 0 negative 96 265 plus 0 RDY RDZ plus 0 530 negative 192 is equal to 0, 0, 0. And the moment equation says 0, 0, 0 plus 397 negative 1060 negative 384 plus 0 negative 7 RDZ positive 7 RDY plus negative 265 1728 4770 is equal to 0, 0, 0. So that's the way we always set this up. And now there's two things we have to notice here. One comes up pretty often, and the other one, this is the only problem it comes up like this. So the first thing, the easiest thing to make sense out of is the x component of Newton's second law gives 0 equals 0. And so we don't want to include that in our system of equations. That doesn't help anything. So if we count up our variables, we have 1, 2, 3, 4 total variables. We had 6 equations. Now we see we have 5 equations. Okay. But now the other thing that's a little more subtle in this problem is if you look at what would happen with this problem, this 96 here and this 192, those wouldn't produce any moments. Okay. But the 265 and the 530, those would produce moments. In other words, this thing is going to start to rotate about its axis. Okay. There's no couple applied about the x-axis that counteracts those two moments, that keeps it at rest. If you apply those two forces, this thing is going to start to spin. And so we don't want to assume that all the moments add up to 0 about the x-axis. Okay, we can't assume that. It actually is there is going to be some net moment, and that's going to cause an angular acceleration. So we just want to ignore the x component of the moment. Okay, we don't, along the x component or about the x component, we're not in static equilibrium. So we also want to ignore this equation. About the x-axis, it's not static. Yep. Yeah, if you just look at that equation, you just see that there's no load that makes that static, and you just end up with an equation that says positive 100 something is equal to 0. That's obviously not true. So that's how you would notice it mathematically. But if you look at the problem, you can also make sense out of it. So now we have 4 equations and 4 variables. And I'm going to write out a table to solve this for a matrix. Okay. 4 equations. So here's equation 1, 2, 3, 4. And the variables, I'll go in order R, C, Y, R, C, Z, R, D, Y, R, D, Z, and then here will be the constants. Okay, so equation 1 says R, C, Ys, we have one of those. Our dy's, our dy's, we have one of those. And then the constants, 530 minus 96 is 434. But that's still on the left side of the equation, so we have to move it to the other side. So our constant is negative 434. And then the second equation says RCZ, we have 1. RDZ, we have 1. And the constant is 73. But then we move it to the other side and we get negative 73. Then equation 3, RDZ, we have negative 7 of those. And the constant is 668. Move it to the other side, so negative 668. And then the last one, RDY, we have 7 of those. And 4, 370, 4354. Negative 4354. Okay, so now if you have a TI-89, you probably have a simultaneous equation solver that makes it a little nicer to enter that in. You can do it that way, or if you have an Inspired, there's probably something like that. If you have an earlier model, then you can just enter that as a matrix and use reduced row echelon form. I guess we might as well. Okay, so number 13. Okay, so you have this thing like this, and it's connected to a shaft that goes through. Okay. And there's a bearing over here. That's a pin joint. And there's a bearing over here. There's a cable connecting this end to the ground. And there's a force of 600 newtons this way, and a force going back this way of 750 newtons. And then the dimensions, this distance is 200 millimeters. I'll just put them all in meters. So 0.200 meters. This distance is 0.2 meters. This distance is 0.25 meters. And then this is 200, or 0.2 again. And then the last thing is the height here. That height is 0.2. Okay. Can everyone picture what this is supposed to represent? Yeah. And Does it give a coordinate system? No. And it says that this bearing provides thrust, and this bearing, no thrust. And we want to calculate the reactions. So free body diagram. Looks like that. That's the outline. And then we have the forces up here, 600, 750. There's a cable attached to this point, so that's a force this way. I'll call it T. And now, again, those are pin joints. The one over on the left end provides thrust. So that one produces 3 force vectors, 3 components of force. I'll call that RA. The one at the other end doesn't produce any thrust, so that's just going to have a component this way and this way, no component along the axis. So I'll call that, well, I'll call this RB. We haven't chosen a coordinate system yet. And then we have to think about the couples. Do those 2 pin joints provide any couples? No, and the reason they don't provide any couples is because they share the same axis, and if you have 2 pin joints that share the same axis, they don't produce any couples. Yeah, well, you know, so yes, if these 2 had different axes, then the fact that they were pin joints wouldn't even be useful, you know, because it wouldn't be able to turn. Like if you have 2 pin joints, they need to share an axis, or else there's no reason for that to be a pin joint. It would be something else. Okay, so let's, for a coordinate system, let's put it right here. So I'll say X is that way, Y is this way, Z is this way. And then we can put the about point at that same spot at A, where the origin is. Okay, so now we can calculate the row vectors, the force vectors, and the moments. So first, the force RA, that's at the about point, so there's no row vector. That's RAX, RAY, RAZ. And the moment is 0. Then we have this cable force. The row vector for that is, so it's 0.2 meters in the positive x direction, and then 0.2 meters in the negative z direction. So rho is 0.2, 0, 0.2. that cable force is in the negative y direction. So that's just 0, negative t, 0. And so the moment we have positive 0.2 t for x, 0 for y, and negative 0.2 t for z. And then the 750 and the 600, the row vector of that point so we have to go in the positive x direction 0.2, 0.25, so now we're at 0.45 in the positive x direction. And then we have to go 0.2 in the positive y direction, and none in the z direction. So the row vector is 0.45, 0.2, 0. The force vector is 600 in the positive x, 750 in the negative z. Okay, and that cross product is negative 375. Yes. And then I can't do this. I already calculated RBX, so you guys do the rest, okay?
We got the negative 600 for RAX.
Okay.
And negative 415.4. Negative 519.2. 415.4. 519.2. 750.
Okay. There's not much we can do to sort of sanity check this answer, make sure it makes sense. Because these components of RA and RB, those can be positive or negative. But we do know that any cable tension has to be positive. And so the fact that that 750 is positive gives us a little more confidence. What you could do now, if you were doing a problem where it was really important to get the right answer, you know, like at work or or for a research project or something, you could take these answers, plug them back into Newton's laws, and make sure that you come out with zeros, you know. But yes. Okay, yes. So the way this works is we are assuming that this force is down in the negative y direction. And so a positive value of t means the force is down. When we express that as a force vector in here, we thought of that as a positive value t times a unit vector in the negative y direction. Okay? Our unit vector was 0, negative 1, 0. And so if we come out with a positive answer for t, that means that the force is down. And you can see that if you look at Newton's second law. So we got that force of 750. But if you plug it back into the force vector that applies, 0, negative 750, 0. So cable tensions should always be positive, but then if you plug it back into the vector in Newton's second law, you'll see what the force vector is. And it is down. Any other questions about that one? Yes. Mm-hmm. Mm-hmm. Oh, you matched the solution, and well, dang it. Yeah. Would be RBY. So RB, I don't know. So, you know, we were just talking about it today in office hours, how there's like a million things you have to do, and one mistake messes up all the answers. So that's sort of painful. That's why now, so on a test, you wouldn't do this probably, you know, and if you had a number wrong, you know, your numbers were wrong, but you did the steps right, you get full credit for it. But if you had to get this answer right, now you take those, plug them back into the original equations, and if it doesn't work out, then you have to do it again, you know. That's just sort of how it is. It's sort of a pain. Okay, but my RB was the same. My RAY was 334. Yeah, that's what I got. And then my RB was 230. You just this minute got that same thing? Yeah. Oh, okay. Oh, okay. Oh, okay, so what were the answers? Positive. Instead of negative 519. Positive 230.8. Okay. Oh, okay. And that's the answer that's in my solution? Okay, so that sounds like that's the right one. Okay. Any other questions about that one? Any other homework problems you want to see? Well, let's, if you don't have any that come to mind, let me just make up a couple, well, maybe just time for one, but I'll make up a problem and you can just work on it together with the people you're sitting near. You know, it's a chance to make sense out of some of this stuff. So let me do two-dimensional problem. So let's say there's a pin joint there. And you have this L-shaped structure. So let's say this is a meter. This is half a meter. And this is 1.5 meters. And let's say there's a force applied this way of 1,000 newtons. And at the end here, there's a roller supporting the end against the floor. What are the reactions? Okay, so the first thing, this is important. If any of you didn't draw a free body diagram to save yourself time or whatever, that's a very bad habit. So if you didn't draw a free body diagram, then that's the most important thing you learned in this whole class today. Don't do that again, ever. Okay, so I still like people write me messages like, I'm in dental school or whatever now, like, you know, people in my regular classes like, hey, how's it going? I'm in dental school. And I'm still like, you still draw free body diagrams before you use Newton's second law? Okay, so there's a 1,000 Newton force here. There's a force vector here. I'll call that RB. And then from the roller, there's an upward force. I'll call that the scalar RA. And the about point I'm going to put here. So rho F moment. Okay, so from the about point to that point A, the roller, that's -1, 0. The force vector is 0 RA. And so the moment is negative RA. Then for the force RB, that's at the about point, so rho vector is 0. The force is RBX, RBY. Bless you. Moment is 0. And then for the 1,000, that's 0.5 meters in the positive X direction, 1 meter in the positive Y direction, so 0.5, or 1.5, I'm sorry, 0.5, 1.5. The force vector is -1,000, 0. And the cross product is positive 1,500. So now Newton's second law says 0 RA plus RBX RBY plus -1,000, 0 is equal to zeros. And the moment equation says -RA plus 1,500 is equal to 0. So this tells us that RA is equal to positive 1,500. That tells us that RBY where's that, is negative 1,500. And RBX is positive 1,000. Okay, so let's think back, put this back in the free body diagram and think back what this means. Okay, so here we have an upward force of 1,500. At the pin, we have a horizontal force of 1,000. And we also have a downward force of 1,500. And then up here, we have a force to the left of 1,000. So this 1,000 Newton force is trying to rotate this thing counterclockwise around that pin. To counteract that, we need a force up here that's going to rotate it, try to rotate it back this way to counteract that. But since we can only do it with a vertical force here, that vertical force needs to be balanced out by a vertical force here. Any questions about that? Okay, so today's assignment will just be read today's notes and then keep working on the stuff from last time. Hi.